All right, so, let's see what all I got going on here today. The last mastering for the class is on Monday. It covers Chapter 19, which you are able to do now if you want to. What else we have? Today my plan is to finish Chapter 19, which is the end of nuclear chemistry. And then Monday we're going to review for the final. I have your exams to get back at the end of class. In general, it was good. The class average was a little bit higher than the last test. So good. And your grades are already at mastering, so if you've seen them there. Yep. What else do we have? The final is May 5th at 10:30 in here. On my website, there are final exam review practice problems if you want to start working through some of those, just to kind of get a feel for the style of question they're going to be asking. Remember, it's multiple choice, Scantron, 70 questions in an hour and 10 minutes. So you have to work kind of speedy. Yeah, I give you everything. Give you a little book. You just have to bring a number 2 pencil and a pretty industrial eraser. Right, because in case the Scantron doesn't erase correctly, they'll mark it wrong. So, number 2 pencil, erasers. I'll bring everything else. Last thing, I emailed you guys yesterday. Some of you guys have definitely responded. Thank you, because when I emailed you yesterday, we were at 5% response rate. We're up to 40% response rate, which is still sad, but closer to if your class is able to get to 95% by class time on Monday, I'll bring some delicious donuts to help you study. If not, then we just study anyway. So, things I'm looking for. If you've not filled out your course evaluation, the things I am interested in seeing, is the YouTube video stuff worth doing? I do appreciate that. Do you like the online homework, or is it the worst thing ever invented? Do you ever use the textbook, or should I just go ahead and make the textbook optional? Because that's a possibility that I just make the textbook optional for other classes. Do you like the way I kind of do these notes where it's an overhead projector rather than me writing on the board? I don't know if that's a big deal or not. So just things like that. Things that if you take another class from me, you would like me to do differently or keep the same. Because there's a good chance you'll end up taking another class with me. So the only way I know that you hate it is if you tell me, or you really love it. Otherwise, I'll do something else. All right, any questions on any of these items? Okay. All right, so last time we left off talking about gamma rays. We have first question, Paul.
If we get 100% on the course evals, could you drop the final?
Okay, drop the final. No, but if we get to 100%, I'll come up with something. Maybe I'll drop another quiz or something. Yeah. Yeah, it's kind of thin in here today. I'm going to say there's a good 10, 15 people missing here today. So you may have to rough them up this weekend. Yeah. Yeah, you have everybody's email address because I emailed everybody last night. So you have everybody's email address in the class. All right, so last time we talked about who is the most famous gamma radiation poisoning victim fictional? Bruce Banner, yes. So we are going to talk a little bit about gamma radiation later today and how that is physically not possible. So why that exists only in the comic books rather than in reality. So Bruce Banner, aka Incredible Hulk, for those people who may not be comic book aficionados. All right, so we'll finish talking about other types of radiation, and then we'll talk about some half-life stuff, and then we'll talk about applications. All right, so positron emission is another type of radioactivity that we can use. This occurs when an unstable nucleus emits a positron. This is going to sound like science fiction, but it's not. So a positron is the antiparticle of an electron. So when we notate the electron, right, we do this. How much mass does an electron have? 0. What charge does an electron have? -1, right? So this guy is the electron. A positron also has no mass, but it has a charge of +1. So it's a electron with a positive charge, which is where nuclear chemistry gets a little funky. So when you hear about positron colliders, they're using positively charged electrons to collide into unstable molecules to make new molecules. So how this works is if I have an electron collide with a positron, what would be my new mass? Okay, what's my new charge? What's that guy? A gamma ray. So a positron and an electron collide together to make energy rays. So that's one way we can make gamma radiation. We can also see it if we do what this is, positron emission. So instead of using positrons as a reactant like we are here, we can use it as a product. Bless you. So I have phosphorus degrading into silicon and a positron. All right, so there's one other type of radioactive emission we need to talk about before we can talk about half-lives and how we use these. It's going to be electron capture. Electron capture involves a particle being absorbed instead of ejected from the nucleus. All right, so if I have something like this, if I do, what am I notating here if it's a 1,1p? Okay, proton. And my electron. If I combine a proton and an electron, what is my new mass? Okay, what is my new charge? If it's a 1, 0, which particle is that? Has a mass of 1, charge of 0. Neutron. Right, so if we had an electron and proton collide together, they should make a neutron. So if I have I choose to collide ruthenium and an extra electron in there, what has happened to my overall mass? Right, nothing. What has happened to my charge on the bottom? So it's another way of making new elements. So instead of producing a proton or producing a helium atom, an alpha particle, we slam it with an electron to force it to become a new element. So electron colliders. You can slam electrons into other elements. Yeah. It's not the same thing exactly. Yeah, it'd be more like an isotope. All right, so we'll do a little bit of math. So does everyone have a calculator available, handy? We haven't talked about kinetics in like a month. Clearly too long. So we're going to come back and talk about some kinetics as part of like getting ready for our final. So radioactivity is the spontaneous emission by unstable nuclei of something. It could be an alpha particle, a beta particle, gamma radiation, maybe a positron. All of those emissions obey first order kinetics. So they all have a half-life that's the first order half-life. So that should look familiar. The first order half-life is T1/2, which is the half-life, equals 0.693 divided by K. This is little k, so what does little k tell me about? You may need to start reviewing. Right, that's my rate constant, which is different than my big K. Big K is my equilibrium constant, which is a combination of individual rate constants. Then we also have this equation. We also had that one a while ago. I'm going to apply it specifically to radioactivity. So I have natural log of NT over NO equals negative rate constant times time. NT is going to be the number of radioactive nuclei at time t, so not 0, whatever time I'm measuring out to. And n sub 0 will be the initial number of radioactive nuclei. Alright, so one of the most common ways we talk about kinetics of radioactivity in your everyday, ordinary life would be carbon dating. When we talk about carbon dating, we're using radioactive isotopes of carbon, knowing the half-life of it, back calculating based on how many are now, knowing the half-life, how many were there before. So, let me tell you one or two things about carbon. Alright, so this is my carbon-14 isotope. How do I know it's the isotope of carbon, not regular carbon? Right, I mean, its mass is funky, because carbon usually has a mass of 12, right, not a mass of 14. So I have the C14 isotope. It will break down into nitrogen and an electron. The first order half-life, which half-life means like, right, if I had 10 of these, over the half-life, how many should be left? Right, in 5. So it turns out for carbon, it takes 5,730 years to break down half of the carbon-14s into nitrogens. So knowing the half-life and knowing how many C14s are in there, we can back calculate how many there should have been and then figure out how long that was. So let's say I have a tree sample. I took a core out of a tree and it has an activity of 10.1 atoms per minute of carbon. If a tree that is in good shape and currently healthy has a decay rate of 15.3 atoms per minute, let's figure out how old the tree is. So first thing we have to do is we have to find the rate constant. Alright, so we have this equation that tells us about rate constants. What's the other thing we know about carbon that I told you like 2 seconds ago? Right, we know the half-life. So we know this equals. So everybody get out your calculator, figure out what K is. for this particular sample. Is that a fast rate constant or a slow rate constant? It's pretty slow, right? Because it's to the -4th years, right? Pretty slow. All right, so then we're going to combine that with the other equation we had. All right, so this N0 is initial. In other words, original sample. This is the sample I'm interested in, the NT. We know K, and we're looking for T. All right, we're looking for the time. So we just need to plug in. Then what would be my units on my time? Years. Good. We'll do one more. They're not particularly tricky. There's only 2 equations. We just plug them in. So my next one is as tricky as I can possibly make the question. So it turns out you have a radioactive isotope in every one of your smoke detectors. We all use americanum 241. And it has a half-life of 432 years. I want to know how long will it take for 33% of that isotope to decay. So this is what I'm asking. Let's go through some thought process of what I'm asking first. So if I have 1 half-life, what percentage is remaining? Right, we're at 50%. If I have 2 half-lives, what percent is remaining? 25. If I have 3 half-lives, it's like 12.5, right? So if I do 0.5 to the first power, what's that equal to? You guys are kind of drowsy today. What if I take 0.5 and square it? What if I take, you don't even have to use your calculator at this point, hopefully you see the pattern. If I take 0.5 and I cube it, what's my decimal point? So if I have 1 half-life, it's 50%, which is the same way I'm going to say 0.5 to the first power is 0.5. If I have 2 half-lives, 25% remains, or it's the same as saying half-life squared or half-life cubed. So we'll start off with some easy questions. If I have used up 33% by decaying it, what percentage do I have left? Okay, 67% remains. So if I have 67% remaining, it's similar to how I set up these questions, right? But I'm looking now for the exponent. Over here, I knew the exponent and I found the fraction. Here, I know the fraction. I'm going to look for the exponent. All right, a little bit of math review here also. How do I get the exponent by itself? Regular, boring old base 10 log. All right, if I take the log of both sides, it pulls the exponent out front. I'll skip through the calculations part. Figure you guys got that. All right, so now I know what half-life I'm using. I'm going to use a 0.578 half-life. There is one more snazzy equation we can use that relates this to time. So this exponent tells me the fraction of how much time it has elapsed compared to the half-life. Right? I'm saying I know the half-life is 432 years, and I have 0.57 of it. I should figure out my new time. You could also write like this. Right, because now I have a fraction. I know my half-life is 432 years. I only want 0.5 of that half-life. Figure out my new time. So it'll take 250 years for 33% of American 241 to decay. So a while. So that part of your smoke detector doesn't go bad. It's the batteries. Batteries died long before 250 years. And they always die in the middle of the night, without fail. They somehow know when it's 2 a.m., and that's when they choose to start going off. Things you have to look forward to when you own your own house. Figuring out, how do I find a ladder? Can I just sleep through it? Is something really on fire? Alright, so now talking about applications of nuclear chemistry. We're going to work our way through fission, some fusion, and then nuclear medicine is my last application. Alright, so in the early 1900s, Enrico Fermi tried to synthesize a new element by bombarding uranium with neutrons. He found that he didn't make a new element. He instead split the element into two new components. So in this case, he's using uranium-235. And bombarding it with one neutron. He found that it split into barium I guess this is showing a different experiment. This is the one that he saw. Three neutrons and a ridiculous amount of energy. So, while you guys are working on that, let me see if I can pull up my, I'm not sure this video loaded.
Teachers love mousetraps because they're a great lesson in potential and kinetic energy. So potential is energy that could happen,
Yeah.
And then kinetic energy is moving energy.
Okay.
So if we set this mousetrap,
Yeah.
and there we go, and I'm going to put a ping pong ball on it, carefully.
Because mice love ping pong balls?
Well, it's a good demonstration. So when this flips, it'll take all that energy it's storing and release it.
Yeah.
So I'm going to drop this on there, and then we're going to see if we can get that ping pong ball to fly.
Okay.
All right, so here we go. Ready, and... That's a good 30 feet.
Okay, that was a crappy trick, by the way. I mean, that's nothing like the foam or anything. We should have started with that, probably.
Well, we got the idea of that's a lot of energy in one mousetrap.
Yeah.
But what if we picked it up just a little bit and tried it with a couple...
10 million mousetraps?
Well, we'll start with this. Wow.
That's beautiful.
There it is. Your amazing prop department here.
Yeah, boy, they must hate you right now.
Alright, so
incredible.
what we're going to do is we're going to trip this by just throwing some ping pong balls in. We'll see how many it takes to actually start it, and then we'll see if it can release energy.
Should we throw them all at once or throw them individually?
Let's start with one and go from there.
Okay, all
So
right.
it's also actually a model for Newton's third law. It's a model for how fission works. It's a really...
Okay, nothing happened?
You have a law.
Oh, you got a lot. Okay, all right.
Go ahead.
Miller. Oh!
Not the best video. I don't really find Jimmy Kimmel funny. So. But the point was good. So that is how fission works. By shooting in one neutron, you end up with lots of energy and lots more neutrons, right? The more ping pong balls shooting around, which is the principle behind nuclear bombs. So what happens is they have a TNT explosive at the bottom of them. So when they hit the ground, the explosion is like throwing in that first ping pong ball. Provides the first little kickoff. It's then a self-propagating explosion that kicks off more neutrons to react with more uranium, makes more neutrons react with more uranium, which is why so much energy is released, because every time it breaks one uranium, it already releases a lot of energy, which is why these explosions are ridiculously big. Plus, it's shooting off a lot of these extra radioactive materials, which is why a lot of people end up, they're not killed by the explosion, but they're killed by the radiation poison later, because of all the radioactive dust that's now around them.
What creates the radioactivity, the neutron?
No, it's these guys over here. The things they make are still radioactive, and they have much longer half-lives than the thing that started off. And so they either end up with radiation burns, or they'll end up with cancer, really, radiation poisonings, a dramatic form of cancer. Which is why you often read about people trying, like different countries trying to get a critical mass of uranium, especially in the Middle East. What they want to do is get enough uranium together so that they can start making their own atomic weapons, because you need to have so many grams of it in order to start off the self-propagating reaction. So that's a lot of the tensions going on, like how much do you need? Or they use it. You can use uranium for good purposes. You can use it for weaponizing also. So you can also talk about good uses such as nuclear power. We can use fission, like I just said, to make a bomb where you release all the energy all at once. You have one big explosion. We can also release the energy slowly, use it to boil water. Use that boiling water to turn a turbine, which then generates electricity. So we're going to release it slowly as a form of heat. Which heats the water into steam. At that point, you're like any other power plant. Does anyone ever tour the power plant? They're pretty neat. You should go. So gas power plants, electric or coal power plants, the only difference is how they get the energy to heat the water. So you can use any kind of energy you want, but once it heats the water turns into steam. The steam is going to turn the turbine. Which makes electricity. So the difference is you just have to figure out what are the pros and cons of the ways you make the energy to turn the turbine. You could also have a water power plant, like the Hoover Dam uses just straight up water to turn the turbines. You obviously have to have a lot of water in order to be able to do that. The biggest pro for a nuclear power plant is that you need very little fuel to make as much energy as if you had a coal-powered power plant. You need very little. Gives off a lot of energy. The biggest con once it's gone through its radioactive decay, and has now made something that has a very long half-life, but is still radioactive, where should you put that? Now, you don't make very much, right, because you didn't use very much. But the biggest question is, where do you put it? You know, do you just put it in a regular garbage dump? Do you put it into a big old trash can that's lead lined, seal it, just let it sit there? Do you try and bury it? Do you put it in an abandoned mine? These are all options that people are trying to figure out what the best option for where to store it is. Shoot it off into space, make it someone else's problem, wait for it to come back in, and then in 200 years it's, you know, it's totally someone else's problem. Which is probably how we end up with some science fiction movies. So until more research is done on this part, people are reluctant, well, 2 reasons. People are reluctant to build them because they don't know where to put the waste. And 2, people are afraid of them, right? You say the word nuclear power plants, they imagine atomic bombs blowing up in their backyard. They imagine, like on The Simpsons, people pouring big green vats of something into your lake, which is 100% false, right? It's just a little bit of solid material that gets made. It did. The issue with that one, which was poor planning on their part, they built it right on the ocean, and they didn't have enough tall barricades. And so what happens when the tsunami came, it swamped the radioactive portion of their plant. So their fault for building it poorly. Obviously, you can't do anything about tsunami. I mean, can't do anything about that. And so that's the other thing. Like, until we figure out how to build them better, you have to, you know, be more cautious about them. So I'm totally fine with nuclear power plants. It's just a matter of, you know, where do you put them? What do you do with the waste? So don't be afraid of them. No, nothing to be afraid of. I mean, the trade-off is we keep using coal power plants, which has its own set of pros and cons. You know, digging out the coal, the people who have to go down there to dig out the coal, there's some health effects there. All the coal burning, is that better or worse than the radioactive material because you're shooting all that coal material into the air? So, some things you're going to need to think about as future voters. Alright, so we can have fission or we can have fusion. Fusion is what you talk about when you're talking about the big colliders that are in France and Chicago. You're going to combine 2 nuclei to make a heavier nuclei. So in this case, deuterium and tritium. Does anyone know which element tritium is? It's an isotope of helium. So you got hydrogen. Deuterium and tritium are isotopes of hydrogen that can kick out 1 helium, some energy, and a neutron. So I put in 2 nuclei and I get out 1 nuclei and sometimes neutrons, some extra energy. Preferred, yeah, sorry, I got kind of squished together. Fusion's how the sun works, how stars work. That's why they're giving off, the energy that they're giving off is in form of light and heat. They work through fusion of new material. So Star Wars is going to use hydrogen atoms to release heat and light. We have not figured out how to do fusion on a large scale on planet Earth, because it would be a much better method than fission, because you wouldn't end up with anything radioactive. You'd shoot in radioactive things and get out just energy, light, and some helium or hydrogens. That'd be awesome. I haven't figured out how to do that on a scale bigger than 2 or 3 atoms at a time. So, area of research that they're still working on. All right, radiation in everyday life. Let's see what I have. All right, so you may have heard of how we measure radiation. So you talk about rads or REMs. So radiation absorbed dose is a rad, where a rad is 1 × 10⁻⁵ joules per gram. We also sometimes talk about a REM, which is a way of converting this rad, which is hard to think about because it's in joules per gram, into a measurement of how bad it is for you. So an RBE is what this is over here. Relative biological effectiveness. So it's a way of figuring out how bad this particular type of radiation is for you. So looking at my scale, what is the worst type of my 3? Right? It would be the most damaging. Except it's such a large molecule, it can't get through your skin. So it can cause a lot of skin damage, but it can't cause any internal damage. Right, because alpha particle is like a whole helium particle. Then beta and gamma rays are equivalently damaging, and both of these can pass through your skin and affect your internal organs. But we'll talk about here in a second why gamma rays are actually good and bad. Good and bad. This is just a table from your textbook saying average doses of radiation you're exposed to every day. So this is in millirems. So a rem over here was how bad it was in general. Your normal radiation exposure is 1,000 times less than any of these things, so millirems. Right, so if you took a 5-hour jet plane ride, you would be exposed to 2.5 millirems. If you decide to stand in a closed room with radon gas, that would be worse, you would get 200 millirems per year. You need to get 100 millirems, no, 100 rems, sorry, 100 rems, not milli. You need to get 100 rems to be considered radiation poisoning. So you have to get a lot more. You'd have to take like 1,000 trips on the airplane, just around and around and around the Earth, really quickly to get radiation poisoning. Even your diagnostic medical procedures, right? The chest x-ray or dental x-rays, 30 millirems, you have to get thousands of times. You'd have to just stand pretty much in front of the x-ray machine for about an hour, probably, to have some skin damage. Same thing if you decide to smoke a lot of tobacco. When you do like 30 cigarettes a day, you are getting close to radioactive poisoning just because it's in the plant. And so when you smoke it, it releases it.
Wait, you need 100 milligrams or you need 100 grams?
100 rems. 100 rems. All right, so let's talk. Last thing today will be some applications, uses in medicine. I don't know what's going on with my camera today. We'll just do that. A little bit of this. Okay. All right, so useful in medicine. A few different ways we use it. These are some common radio tracers: Tectinium-99, iodine-131, Thallium-201, fluorine-18. They have very short half-lives comparatively, right? Carbon, we have 5,000-year half-life. Americanum have 400-year half-life. These are all measured in hours or days, which is why they're used in medical applications, because they don't last very long in your system. So common procedures would be something like a PET scan. It's a positron emission transmission scan, where you're gonna ingest fluorine-18 orally. You drink that. It would travel preferentially to the heart and the brain. And then has anyone ever had a CAT scan, MRI, something like that, where they slide you into the machine? Same machine. They're going to slide you in, and they're going to watch the positrons shoot out of your body. And then the computer will calculate back to what part of the body it was coming from. And so, especially for heart and brain, that's looking for cancer, because preferentially those fluorine molecules will be absorbed by molecules that are being divided quickly. Another thing you can use a PET scan for is you can have a radioactive glucose molecule, which is for general cancer measurement. Right, because cells really need glucose when they go to divide. So they put in a radioactive glucose molecule. They'll put you in a PET scan thing and see where that glucose is being used mostly. And they'll be able to figure out what the appropriate cancer treatment is. Surgery, right? If it's small, you can cut it out. If it's not small, they can do targeted gamma radiation. So if it's just in your lungs, they can just apply the gamma radiation to your lungs and try and kill off those cells. If it's pervasive, like leukemia, you will take chemotherapy. You'll ingest one of these radioactive molecules. Sometimes it's an IV drug. And it just kills off all the cells. I have one quick video that we have time for that kind of explains the difference between those three and how chemotherapy and whatnot works.
We all start life as one single cell. Then the cell divides and we're 2 cells, then 4, then 8. Cells form tissues, tissues form organs, organs form us. These cell divisions, by which we go from a single cell to 100 trillion cells, are called growth. And growth seems like a simple thing because when we think of it, we typically think of someone getting taller, or later in life, wider. But to cells, growth isn't simple. Cell division is an intricate chemical dance that's part individual, part community driven. And in a neighborhood of 100 trillion cells, sometimes things go wrong. Maybe an individual cell's set of instructions, or DNA, gets a typo, what we call a mutation. Most of the time, the cell senses mistakes and shuts itself down, or the system detects a troublemaker and eliminates it. But enough mutations can bypass these mistakes, driving the cell to divide recklessly. That one rogue cell becomes 2, then 4, and 8. At every stage, the incorrect instructions are passed along to the cell's offspring. Weeks, months, or years after that one rogue cell transformed, you might see your doctor about a lump in your breast. Difficulty going to the bathroom could reveal a problem in your intestine, prostate, or bladder. Or the routine blood test might count too many white cells or elevated liver enzymes. Your doctor delivers the bad news. It's cancer. From here, your strategy will depend on where the cancer is and how far it's progressed. If the tumor is slow growing and in one place, surgery might be all you need, if anything. If the tumor is fast growing or invading nearby tissue, your doctor might recommend radiation or surgery followed by radiation. If the cancer has spread, or if it's inherently everywhere, like leukemia, your doctor will most likely recommend chemotherapy, or a combination of radiation and chemo. Radiation and most forms of chemo work by physically shredding the cell's DNA, or disrupting the copying machinery. But neither radiation nor chemotherapeutic drugs target only cancer cells. Radiation hits whatever you point it at, and your bloodstream carries chemotherapeutics all over your body. So what happens when different cells get hit? Let's look at a healthy liver cell, a healthy hair cell, and a cancerous cell. The healthy liver cell divides only when it's stressed. The healthy hair cell divides frequently, and the cancer cell divides even more frequently and recklessly. When you take a chemotherapeutic drug, it will hit all of these cells. And remember that the drugs work typically by disrupting cell division, so every time a cell divides, it opens itself up to attack. And that means that the more frequently a cell divides, the more likely the drug is to kill it. So remember that hair cell? It divides frequently and isn't a threat. And there are other frequently dividing cells in your body, like skin cells, gut cells, and blood cells. So the list of unpleasant side effects of cancer treatment parallels these tissue types: hair loss, skin rashes, nausea, vomiting, fatigue, weight loss, and pain. That makes sense because these are the cells that get hit the hardest. So in the end, it's all about growth. Cancer hijacks cells' natural division machinery and forces them to put the pedal to the metal, growing rapidly and recklessly. But using chemotherapeutic drugs, we take advantage of that aggressiveness, and we turn cancer's main strength into a weakness.
So, hopefully that explains some of the difference between radiation, chemotherapy, because chemotherapy has all of it, and some of the side effects. So, that would be why cancer patients usually have no hair. It's killed off. All right. I have